Okay, I'm going to go over the handout that we did in class. This is also located on the class website, and I'm going to talk you through how to solve for the rates of motion for plate tectonics. So here's what we're looking at. We've got this handout here, and I'm going to talk you through the answer key. So we're going to calculate and do all kinds of numbers and make sense of this. So here's where we're at. We're looking at these pictures right here. Here I have two pieces of continental crust. I'm simply just using my key here to make sense of it. Continental crust of granite. This rift zone is opening up here. Remember, rifts are what break apart continents, like in Pangea. Rifting began, and that led to the formation of oceanic crust. And so this is picture A, where the rift zone is opening. Picture B, oceanic crust is forming, and this plate is moving to the right, and this plate over here is moving to the left. And we're really viewing kind of continental drift in this within this picture here. And then letter C is just more time has taken place, and so notice letter W here, which was really close to the Rift Valley, here is much further apart. So now we have letter C, and those are the pictures down here. So we have new oceanic crust. We're forming right here along the rift zone. This is what's labeled here, this axis. We have lithosphere, that is the solid portions of the upper mantle and crust. And we have this asthenosphere, that's this code, that's this layer right here in all of these pictures. And lastly, we have sediments. So we have sediments piled up over here. So we'll talk through these. So here goes. So number one says the figure below illustrates different states of the formation of an ocean basin and subsequent separation of two continents via the process of seafloor spreading. So which represents older seafloor, C or W? Well, W does, because it's further from the rift zone. So if I look at these pictures here, W formed first, and then as plate tectonics and this ocean floor continued to evolve, we see that it's traveled further. So letter C is much younger. It's closer to the ocean ridge, so therefore it's going to be, let's just say, closer distance, it's younger. Further distance, it's older. So my next question is, well, what do the magnetic stripes, or what do the stripes in the younger basalt ocean represent? And what and why does this occur? Well, these are the magnetic orientation. The iron-bearing minerals that align within the Earth's magnetic field upon crystallization. We learned once upon a time ago that basalt is composed of highly mafic minerals, and these are iron-bearing minerals. And they align themselves like little compasses. So they tell us the Earth's magnetic field at the point at which these particular rocks solidified or crystallized as they went from a liquid to a solid. So when I get these alternating layers here, these stripes represent the relative magnetic field at the time in which they solidified. So what are the stripes in C and W? Why are they equidistant on the ocean ridges? Well, we assume that the spreading rates are equal, they're traveling at the same rate. And as a result of that, if they travel at the same rate in the same amount of time, they should be about equidistant. And we see that W is about this distance here, where W on this side is about the same distance, and where C is located about the same distance. So they're kind of like mirror images of one another. We're simply assuming that the spreading rates on both sides are equal. So why do the sediments of overlying basalt layers thicker? Why are they thicker further away? Well, it's had greater amount of time for sediment to be deposited and accumulate along the ocean floor. So if I look at this picture here, sorry, I'm kind of losing control of that. I have a deeper sediment layer further from here, where I'm going to have a really shallow or thin layer of sediment directly near and along the oceanic ridge. So sediment are going to pile up. They have just more time to accumulate on the ocean floor. So in figure C, the stripe mark C on either side has been dated to 10 million years old. Using the given scale, what is the rate of movement in centimeters per year? Show your work. So if I know that the key here says 1 millimeter equals 38 kilometers. So 1 millimeter equals 38 kilometers, and I measure them directly, and I find that C is 5 millimeters away, I find that this equates to, if I set this as a proportion, 1 millimeter equals 38 kilometers, 5 millimeters equals 190 kilometers. Well, now I need to convert kilometers into centimeters, and I know that there are 1,000 meters in a kilometer, and there are 100 centimeters in a meter. 100 times 1,000 is 100,000. So I can take 190 times 100,000, and I get 19 million centimeters. It traveled 19 million centimeters in 10 million years. So the rate of this plate motion is going to be 1.9 centimeters per year. So if your calculations were close to that, I would say between 1.5 and 2 centimeters per year. So let's move on to question F. If this rate of spreading has been constant, what is the age of the rocks at W? Well, these are about 70 million years old, and here's how I know. If I measure them directly, it's 3.7 centimeters or 37 millimeters over 1 times 38 kilometers per 1, this should be millimeter, tells me it's 1,406 kilometers away. Well, 1,406 kilometers over 1 times 100,000 centimeters per kilometer tells me that it's 1.406 times 10 to the 8 centimeters divided by 1.9 centimeters per year. This is the rate that we solved from above, the problem before, tells me that it's 7.4 times 10 to the 7th years old, or about 74 million years old. So I would say about 70 is close enough for this. Moving on to the next problem. The figure below is a geologic map of Southern California showing the San Andreas Fault. Put arrows on opposite sides of the fault showing relative movement of the plates. Label the plate that you have placed arrows onto. So let's look at this picture. Here I have the Pacific plate. The Pacific plate is moving northwest relative to the North American plate that the arrows would be drawn to the southeast in this direction. So this is the North American plate along the San Andreas Fault is grinding up against the Pacific plate. So here's where the problems pick up. It says the rocks marked M at the bottom of the map are 25 million years old and have been cut and separated by the fault movement. What is the rate of movement in centimeters per year? So if I measure it directly, I get 360 kilometers, and I just simply measured from, come on, letters M. So M is this rock here, coincides with this rock here, and these were once connected, and it's the fault. I know that the Pacific plate's moving this way because M is now up here when it was once down here. So I know that the Pacific plate is moving northwest. I'm simply aligning letters M, which happen to be these type of rocks right here on your handout. So if I measure this, I can measure that 360 kilometers. I'm using the scale at the bottom of the page, and I find that it's about 360 kilometers. Is that what the value was, I believe? And I just measured this directly. I measured from the bottom of the M to the bottom of the M. And your numbers could vary if you measure from the top to top, but they're going to be close. Our rates are going to be about the same. So here goes. 36 million centimeters, right? 360 kilometers. There's 100,000 centimeters in a kilometer. It's 36 million centimeters divided by 25 million years. Tells me that the rate of movement is about 1.4 centimeters per year. So roughly between 1 and 2 centimeters per year. So the rate of annual movement along a fault that you calculated is really very small. So why are earthquakes so devastating to land features or land structures? Well, plates move in a series of jerks. They're sudden energy releases, right? This energy is released very suddenly, not in one smooth motion. So such motions release stored energy. And this is tremendous amounts of energy. So when they move very abruptly, and they release pent-up energy that's been stored for hundreds, thousands, tens of thousands, even up to millions of years. So here we go. So letter D says the actual movement along the fault during the 1906 earthquake is estimated to be 5 meters, which is 500 centimeters. Using the average annual rate, how frequent is this type of earthquake? Show your work. So the time is going to be distance divided by velocity. So if it moved 500 centimeters and 1.4 centimeters per year is the rate at which it moved, I get about 357 years. So these are not very common on the human time scale, but very common over geologic time. So we can say that about every 300 to 400 years, we get a major plate movement, or in this case, releasing tremendous amount of energy about every 300 to 400 years. And last but not least, in figure below here, we're showing the distribution of the Hawaiian Islands, including the age of each island. So you'll see, when I look at this picture here, oh, come on. All right, here it goes. So here I have Kauai, 4.7 million years old. It's been radiometrically dated. Remember, this is a basaltic flow, so basalt is an igneous rock. It can be radiometrically dated. Notice that if I measure from this edge right here, the leading edge of Kauai, to the lagging edge of the big island of Hawaii, I get a particular distance here, and that distance that I got was 560 kilometers. If I multiply 560 times 100,000 centimeters per kilometer, I get 56 million centimeters divided by 4.7 million years. I find that I get a value of about 11.9 centimeters per year, or about 11 to 12 centimeters per year. That's the rate at which the Pacific plate is moving over the hot spot that is located directly beneath the Pacific plate that leads to the building of the Hawaiian Islands. So how does this rate, this 11.9, compare to the 1 to 2 centimeters per year from the activity from before? Well, it's very high. It's moving much faster than the other measurement. In other words, the Pacific plate along the moving over the hotspot is moving very, very fast relative to, right here, 11.9, relative to the Pacific plate moving along the San Andreas Fault, the transform fault, relative to North America. So we've got different rates of plate motion. So the North American plate is actually moving to the northwest, but the arrows drawn in the activity show it's moving southeast. Well, why is that? Well, since the Pacific plate is moving much faster, right, roughly six plus times faster, the relative motion of the North American plate is southeast. So if I'm looking at the plate, if I'm standing on the Pacific plate and I'm moving this direction, I see the North American plate as moving this direction. So technically the North American plate's also moving northeast. It's just moving northeast a lot slower than the Pacific plate is moving northeast. So therefore the relative plate motion is going to seem like the North American plate is moving southeast. And there you have it.